And welcome back to Calculus 2. We are starting the power series. All right, this is really powerful stuff. I'm going to summarize the entire chapter in one sentence. Change any function you see into a polynomial. Done. Now, just imagine how easy it is to differentiate polynomial, integrate polynomial, take the limit, do all of the things with polynomial, except finding roots. That's really pain in the neck. But the rest of the stuff, wow. Do any calculus on a polynomial is a joke in comparison to x times e to the x, or x cubed times sine squared x, or something like that, right? Imagine turning all of those, where you have to use all of these exotic techniques, right? You turn all of those into a polynomial and then integrate or differentiate. So the goal of this chapter is to show the process, why is it possible, and then what you can do with it. So that's technically what it's done. Now, for some reason, our textbook has 4 sections on it, which are actually 2 sections. I already said that sections 1 and 3 are technically the same, and 2 and 4 are technically the same. So I was tempted to do 9.1/9.3, but then it's a lot of confusion. So let's just have them in order. Power series. So we are going to talk about, first we're going to have a little introduction about the progression in mathematics, right? You first learn the number, 7, let's say. Then you learn how to add 2 numbers. 7 plus 3 is 10. And then you, instead of writing 7 plus 3, you write x plus 3. You go that extra step, which is you create a function, right? So that's your progression in mathematics. You start by learning numbers, then by learning operations, then by having functions, which contain variables, numbers, operations, and everything there, right? And then you do calculus with it. Parallel world to that is sequences, a list of numbers, series, sum of the sequence, which is operation numbers, right? And now power series. We are going to introduce x inside the series, making it a function. Make sense? So we are now going to take just a regular series that you see in sections 8, 3, 4, 5, and 6, and we are going to embed x somewhere. And it becomes a power series. So what is a power series? The general form for power series is going to be some coefficient ck times x to the k. You can start at 0, go to infinity. So this would be the most basic form for power series. What are its terms? Well, when you have k equal to 0, you just have c0. When k is equal to 1, because series you go plus, c1x, c2x squared, plus c3x cubed, plus ... forever. Because it's infinity. Do you all see it's a polynomial? You see it's a polynomial, right? Because you got that, if you just give c0, it's a constant, and then c1x plus c, it's like y equal mx plus b, right? And then with the x squared, ax squared plus bx plus c. So it's a polynomial. Now, we actually want to study more general case, which actually centers this power series, we'll see what it means, at any value on the number line. So the actual one we want to study at all times is ck x minus a to the k from 0 to infinity. This is the one that we want to pay attention to. And we again have c0 plus c1x minus a plus c2x minus a squared plus C3x minus a cubed plus going on forever to infinity. This one will be known as power series centered at x equals a. Centered at a, value a. Now we'll see what that means. We are concerned with polynomial approximations of functions. What I am claiming is that I will be able to use this in some way to represent e to the x squared, sine x, e to the x times sine x. Anything that you can think of that you learned so far in terms of functions, I will be able to write them in terms of this series. And ultimately as a polynomial, right? Which I can differentiate, integrate easily. So now, I want to remind you of a thing that you already know, which is linear approximation from Calculus 1. The tangent line problem, right? So if you are remembering the tangent line, which was linear approximation, you might remember the formula that looked like this. That's this. Right there. That much of our polynomial approximation. And we know that that already gave us pretty good results when we were approximating the values of a function. So now, I would like to say, why not add another term and have a better precision, and another term to have a better precision. So we are not learning the new thing on its own. We are extending what we know from before. We are building up on what we know. And we are going to see the progression from the first term being computed as a function, then at the first derivative, then at the second derivative, and the third derivative, and the fourth, and the fifth, and so on. So there's going to be this derivative taking, again, very important to kind of get these functions going. So what would be now, in extension to this, I'm going to use green, quadratic approximation now. I actually think I never used green color. This is the first time officially for me in 3 years. It's always first time, right? Shall we call it Q of x? It's going to be f of a plus f prime of a times x minus a. And here is the quadratic term, the new one. There it is. So this would be quadratic approximation. So let's use this to approximate something that we don't know right off the bat. What would you use calculator for to compute?
7 equals 5 times 2 the r squared.
EX squared.
I'm sorry?
E to the x squared.
No, not the function, a number. Let's say e squared you would use, right? E squared, you would use, or e cubed, you would use a calculator, or ln5, you would use calculator, or square root of, I don't know, 17, you would use calculator, right? So pick something like that you would use calculator for, and then let's unleash both of these methods on it, and also the calculator, to see how well they do. So let's pick something, anything.
Before we do that, I have a quick question.
Yes.
For linear approximation, it's using like f prime, but when we go back to the
Power series expansion?
Yes.
You just says C1, C2. That's C. Observe that all of these F's have A in there. So this is a number. It's not a function, right? And I can just call it C2. Because it's computed at A. A is going to be whatever number you want to find, right?
So
That's
it's
close.
square root of 9
Square root of 94. Why not? That was a save. Yeah, it was a save right there. Because square root of 9 is 3. I'm done. It's just like deflect, deflect, deflect. Got it. 94. All right. So here is the deal with this stuff. You're looking at this square root of 94, and you say, I know that the function for this, associated function to this is, the pen just died. A second, there we go. Function f of x is the square root of x. That's the function. And I also know that this a should be 100, because it's easy to find the square root of 100. The other close number is 81, but 81 is 13 away from 94, where 100 is 6, right? So it's closer to 100 than to 81. So let's use 100 as our number. So that's our A. And now I want to use linear approximation first. So I will have, I'll write it, f of a plus the derivative of a times x minus a. Now, I'm just going to write on a side all of the important things. So f of x is square root of x, f prime of x is 1 over 2 root x when you take the derivative. You should know how to take the derivative. A is 100 and x is 94. So these are all of the features that you need to compute the value. All you need to do is to plug all of this in and just come up with a number. So how much is L of 94? You are trying to approximate square root of 94, but through linear approximation, so L of 94. Well, it's going to be f of a, which is the square root of 100, plus 1 over 2 square root of 100, right, because a is 100. F prime is 1 over 2 root x. And then you have 94 minus 100. We plugged in f of x for f of x, f prime of x to f prime of x, right? All of those things. 94 for x and 100 for a. Compute. What happened? 7 over 10. You have 10 plus 1 over 20. And then this is negative 6, right? So we have 10 minus 3/10, which is 9 and 7/10, which is 9.7, right? Is that good? 9.7? Now let's use the abacus. What does the calculator say?
9.695.
All right, 9.695. Can you give me, let's do 5 decimals.
Then add 36.
Like this.
Yeah.
Awesome. I would just say pretty damn good, right? On a square root of 94, this linear approximation, we did not need the calculator at all, right? Stick in a sand on a desert island works just fine. Guys, next time you go to the shore, stick in a sand. People will flock to take the picture right there of you, a young prospective scientist at the shore, playing in the sand.
It's also a good way to get sand kicked in your face.
Sure, sure. Travel in packs. Do it together. All right, so let's now figure out the second, right? So we want to do the approximation, quadratic approximation. So if the first derivative was 1 over 2 root x, I'm going to rewrite that as 1/2 times x to the minus 1/2, and then take the derivative of that for the second derivative, copy 1/2, bring negative 1/2 down, and then x to the negative 3/2, which is negative quarter, oops, sorry, negative quarter x to the 3/2 in denominator. So what's the formula for quadratic approximation? It's going to be f of a plus f prime of a x minus a plus f double prime over 2 computed at a x minus a squared. Now, did we all agree already that this piece over here is already 9.7? I don't have to compute that again from linear. It's right here. So all I need to do is to compute plus this piece. So what do I have? I have 1/2 times negative 1 over 4, and then I have 100 raised to the 3/2 times 94 minus 100 squared. So I have 9.7 plus, I have negative 1 over 8 times 1,000 times 36, right? Which is equal to 9.7 minus 36 over 8,000. Which equals 9.7 minus now 36, and I should have canceled earlier. I can cancel by 4, right? Get the 9 and 2,000. 9 over 2,000. So how much is this?
I feel like I was going to use a calculator anyway to do that. Might as well just use
Desert island, no calculator, cell phone, no charge, no signal, and Wilson is gone. You have nothing else to do. Nothing else to do.
That's the answer then. 9.7 minus 9 over 2,000. That would just be the answer.
I wouldn't.
No, what is it?
I have something to do. Figure out how I'm going to eat.
This is what you need to reinvent the agriculture.
Or figure out if
1.6955.
Okay, so I want to put this in perspective. Calculator, so square root of 94. Calculator gave 9.69536. Linear approximation gave 9.7. Quadratic approximation gave 9.6955. Clearly, quadratic did better. Why? Because it has extra term. If I am to add another term, it will be even better. No, we're not going to do it. Because, actually, do it and then tell us what the answer is, since you volunteered. It's going to be, I'll give you the third term. Just write down what I'm telling you now. That's going to be the third term. F triple prime, so third derivative, computed at A, at 100, divided by 6 times x minus A to the third power.
How are you choosing the denominator?
It's a factorial of the number of the derivative.
Okay.
So you have 0 factorial, which is 1, 1 factorial is 1, and then on the second derivative divided by 2, 2 factorial, and then 3 factorial is 6, 4 factorial 24, 120, 720, and so on.
The denominator is factorial.
Factorial, yes, of the number that you have on the derivative. And you will see the formula is so beautiful in terms of all of the numbers match across the board. It's really beautiful formula. So now we arrive at writing down Taylor polynomial. Sense the tone. And if you don't find this the coolest thing you ever seen in your life, I just don't want to know you. Taylor polynomial. F of x is equal to the summation where n starts at 0, goes to infinity, for the nth derivative computed at A divided by the n factorial of x minus a to the n.
Wait, what? F?
If you ever want a tattoo, this should be it. All right?
That's how the formula works, like the linear.
Yep.
Quadratic. Gotcha.
All of the approximations that you think of, the linear approximation, the quadratic, cubic, and so on, they're all in here. Let's expand this and think about this. First of all, I need to mention that the 0th derivative of x is actually f of x. There's no derivative on it, so it's just a basic function. And also 0 factorial is 1. You don't believe me? Look it up. It is. I really don't have time for it, but that could be the next class, if I have time. So these are the two things good to know. I don't want to box this because in that case, like this is what needs to be boxed and.
So 0 factorial and 1 factorial is the same?
Yes. Because the best
0
answer.
times.
No, factorials all start 1 times 2 times 3 times 4. There's no 0. 0 factorial is 1.
Okay, I'll take your word for it.
Thank you. Okay. So let me expand Taylor polynomial. Summation of nth derivative computed at a divided by n factorial of x minus a to the n. We start at 0, go to infinity. Let's go with the first term. First term is everything is 0. 0th derivative divided by 0 factorial, which is 1. 0th derivative is its original function computed at a. So I'm going to write it here and then erase it. I have a 0th derivative computed at a divided by 0 factorial with x minus 0 to the 0. Okay? Oh, sorry, x minus a. It's just f of a, yes. It's just f of a. Very good. Because this thing raised to the 0 is going to be 1, right? This thing over here is 1. And the 0th derivative is just says no derivative on this f, which means it's a function, its original function. So the whole thing, when it's 0 around, it's just f of a. Plus 1 factorial is 1. So you just have the first derivative, right? Because now n, which is the order of the derivative, n is 1. So first derivative there, computed at a, divided by 1 factorial, which is 1. And then you have x minus a to the 1. That's your linear term, right? And then you got quadratic. So plus, I go next line, f second derivative, right? Because now n is 2, divided by 2 factorial, which is 2, and then x minus a squared. Plus, this is where the third derivative comes in, divided by 6, 3 factorial, 1 times 2 times 3, 6. Computed at a, x minus a cubed. Plus, I'll do one more term, f the fourth derivative. And now we're switching the notation. Now we start using numbers in parentheses. 4 factorial is 24, x minus a to the 4, plus dot, 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 forever. There is the expansion for your Taylor polynomial. And I hope you saw that so far. 2, 2, 2, 3, 3, 3, 4, 4, 4. Easy to remember, right? Always the same number all around. The order of the derivative divided by the factorial, and then exponent on x minus a. That's all it is. So now I'm going to ask you to use this formula on f of x equals e to the x. What do you get? And use a equals 0. Go. Just plug it in. You have f of x, when it's 0 there, e to the 0, something there. Compute all of these. I'll be right back. I didn't have my break. Oh.
So that's what there is we chose one actually. Is e to the 0.
Yeah.
Right? One. So it'll be 1 plus it'll be 1 plus 1. It'll be 1 plus 1. I got this easy. This is x equals e. If it equals e. Yeah, right? Yeah, right? Isn't it equal e without this? Without x, how can you say what it equals?
No, because when you get the summation, the first one is 1 plus 1 plus 1 over 2 x squared. But
No, it's going to be 1 plus x plus 1 over 2.
how? Because it
X minus a, x minus 0 is x.
oh, so yeah, it's 1x.
It's 1 plus x squared over 2 plus x cubed over 6 plus x is equal to 2 plus x is finally equal to 1.
Yeah, and then it just keeps
So
going.
without this having we're going to find it. If you have x, then you can take together.
So
Let's say you say that e squared, you can find it.
you just start solving it.
So you get like e cubed, but you don't know what the x is.
Yeah.
Once you say the x,
You said no better. But it'll just be, yeah.
we definitely can do a quadratic because every time it's going to be 2 over simplified.
First, then p, if you plug in 1 for x, and then it comes out to easy.
Yes.
What's the x?
You still want the cross.
So we want to find this u. So
No, you will actually find the polynomial in terms of x. A is equal to 0, and
Yeah.
everything will be in terms of x.
Yeah.
So I'm not computing. If I was to compute e to the 7, then every x would be replaced by 7. Right?
Yeah.
So I'm looking for the polynomial which will actually have x. I'm not looking for a number. This is actually practicing the art of plugging into the formula, right? And you can simplify, right?
what would you write for 7?
So let's do this problem together. I hope you guys got 1 plus x squared over 2 plus x cubed over 6, right? We got that? Okay, cool. Let's take a look at this. So any derivative of e to the x is e to the x. At least that much is easy. And then as I start plugging this in, e to the x is going to be the function computed at 0, so that's e to the x, plus the first derivative computed at 0 over 1, so just e to the 0, times x minus 0 to the first power. Second derivative computed at 0 divided by 2, x minus 0 squared. Third derivative computed at 0 over 6, going on forever. I'll write also this one. Fourth derivative divided by 24, x minus 0 to the fourth, going on forever. So what do I have? I have that e to the x is equal to 1 plus x plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24 plus dot dot dot. Now, I get to write equal sign over here because of this. Only if you go to infinity, they are equal. If you decide to cut it somewhere, let's say after 3 terms, 4 terms, 5 terms, you cut it at some point and throw away, let's say this much, then you have to put approximated, okay? Not equal, but approximated. Now, this is function computed at a, which is 0. First derivative computed at a, x minus 0 to the first power. So 1, 1, 1, 2, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Always match them. And then you simplify algebra, whatever you get there, but they always match. This is your Taylor polynomial for e to the x. What's the derivative of e to the x? Itself, right? That means that if I differentiate that polynomial, I should get that polynomial. Right? Do I? Hell yes. Look at it. What's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of x squared divided by 2? X, right? Because it's 2x and then 2 is cancelled. You see how it returns itself? These are things that fascinate me in mathematics. Like so much math put into one thing and it just works. Yes? The x cubed over 6, yeah. And when you bring 3 down, it will be 3 and 6 cancel down to 2 when you get the previous term.
It just looks like.
No, it's a 3.
I missed something.
Is it? It's a 3, right? Yes?
Let me show you that one. You were evaluating the first one, we had even zeros. You were evaluating, wait, can you say what you said there again?
In original function, because it's f of a,
Right.
so and we're a is 0, right? So f of a, so that's that one. First, all of them are the same. All of them are e to the x, right? All of the derivatives are e to the x. Original functions e to the x, and all of them are e to the x. Right? So they all get to be e to the 0, e to the 0. Not right. We'll do one more when they're all different. It will make more sense.
And then how do you put these in place?
This one?
Yeah.
Compute it. E to the 0 is 1.
Okay,
E to the 0 is 1 times x.
okay, that's what I want.
1/2 times x squared. Right? Compute them all. What's the integral of e to the x? If you integrate this, do you get that? Hell yeah. Right? What's the integral of 1? X. And what's the integral of x? X squared over 2, right? You see that? That's math for you, right?
What's that one?
Plus c. So it's 1. I know. Somehow math just works across everything all the time. No exceptions. Brilliant. Let's red line now. Enough with the red color. Let's go another example. What else? Oh, sorry. I forgot one important aspect of this. You stare at this and you compress it into a sum if it's possible. Is it possible here? Of course it is, right? We have e to the x to be written as a sum of x to the n if n starts at 0 and factorial. Nice. You see that? We get to compress. So I can write e to the x this way as well. You want to annoy someone in Precalc 1? Just write e to the x this way. All right? It's the same thing. And look at it, right? when n is equal to 0, x to the 0 is 1, 0 factorial is 1, 1 divided by 1 is that term, right? And then when n is equal to 1, x to the 1 divided by 1, and then 2, 2, 3, 3, 4, 4, and so on. You compress them back into this. And that is called the power series for e to the x. And then in the book, they actually give you the table that if you are so inclined, you can memorize for all of the functions. For sine and cosine and e to the x and ln x and ln of 1 minus x and 1 over x plus 1, 1 over 1 minus x, and so on. All of those functions have their power series expansions, and you can memorize the sequences for this, or for each one of them, series. And use them mainly to annoy others. So that's awesome.
And they all start with the base 0.
Yes, they all start 0 to infinity, right? Because the first term is always the original function, and original function has no derivative on it, right? So they all start with 0. They can start in any other one, because as soon as we do, I have my I think I had the differential equations on this one, did I? Like the old notes. I don't have everything here because I was yeah, guys, you have to learn this for the future use. It's not you're not learning this to pass Calc2. So there's differential equations, and here's problem 10. So you have a differential equation which is given like this. For some of you, this is your next semester. This is differential equation, and then you assume the solution as a power series, which is what you just learned, right? And then you take the derivative of that power series, which is going to look like this, and then you shift the counter. Remember shifting the counter? Right there. And then you take the second derivative of the power series, and then you plug second derivative power series here, first derivative power series there, and the original one there. You get this expression. And then you make a mistake, then you forget about that. And then you go and you keep doing it, and you solve some algebra, and then get some recursion equation, and then you expand the recursion equation, and there it is, the solution. Finally, at the end, there's the solution, right? 3 pages later. So next time someone tells you 5 steps too much, here's about 3 problems. This is one of the cheaper problems, right? Introductory example.
Are there functions like that, like the Taylor series don't work?
Yes, and for those functions you can use Fourier series. Fourier series are going to be sums of sines and cosines. So for some of the periodic functions, you can use Taylor series to expand sine and cosine itself, but then there are other functions that are not really behaving nicely, and then Fourier series would be. We do not teach that at RV, and you might see it in undergrad course if you kind of take that kind of math, but it's mainly graduate work. So yeah, Fourier series have its own courses and its own analysis of stuff. So yeah, there's a lot of. There are two graduate courses called Asymptotic Behavior 1 and Asymptotic Behavior 2 that is just devoted to power series. The whole course is built on this. These are the ways to solve partial differential equations and a lot of other stuff. Right now you are learning, in the power series, you are learning one of the most important techniques in mathematics. This power series expansion is the most important stuff, the most powerful stuff that you get to see actually in undergraduate mathematics. What NGIT calls elementary mathematics, okay, through differential equations, elementary math. You're still 250 years behind, okay, with this current, up to the current level. More work to be done. Shall we expand sine or cosine or ln or what? ln? Okay. Let's expand ln. F of x equals ln x. Let's do 4-term expansion. So you know that the first expands. You know that the first term is original function, therefore the next 3 terms are first, second, and third derivative. So let's get all of the derivatives in. The house, what's the first derivative? Great. What's the second derivative? Exactly. What's the third derivative? No, it's positive 2. I am not paying attention. I'm sorry. You have the derivative to do is to plug them in. Again, we'll go a equals 0, expansion around 0.
Infinity times infinity is infinity squared.
You just infinity.
Professor, what are you doing about the plus and of 0?
Just plug in a. Oh, wait.
Yes.
Sorry. 1. Can't compute at 0. No, I'll just give you another 18 seconds to plug in. It's fine. You got this.
Can you factor out the x minus 0? Or don't compute the thing on it?
Yeah, that's what I'm trying to figure. I didn't get there yet. Yep. Or plus 1, whatever.
Yeah. So it's not n over n factorial?
No, it's 1, 2, 3, 4, 5, 6. There it is, ln. And you can also put it into a sum. There's one more concept left, and that is the concept of the remainder. And that would be, remember, okay, here you can see it. Remember how I said I only want 4 terms, right? So it's the original function plus 3 derivatives. Fair? And observe my notation. Very careful about that. ln x is approximated by 4 terms. ln x is approximated by 4 terms. But then, ln x is equal to, I go to infinity. So if you're using all infinity of terms, you have equality between the function that you are representing as a polynomial, right? So equal sign is only if you use all infinity of the terms. As soon as you cut, because you're not elves, right? Sitting there forever calculating this thing in time. So you don't have time for that. You don't have time for homework, let alone to do this, right? If you use all of the terms, it's equal. If you cut it off anywhere, it's approximation. Now, clearly, if you're approximating something, you have error, because it's not the same as the true value. So the difference between the true value and what you have is called an error. And that error and remainder, right, is going to be approximated by the first term you dropped, right? So if I say, give me the first 4 terms, the 5th term, which is the first one you're dropping, is going to contain the most of the error. So you can approximate the error that you are making, well, by that term, the first term you are dropping. So if I say, I would like to know the error for the approximation that has 5 terms. That means that all you need to do is to compute the 6th term, value of the 6th term. Because the first 5 terms is what I asked you to give me, and then after those 5 terms, which we call the tail end, most of the error is accumulated in that next term, the first term you're dropping. So we are simply going to define this remainder Rn of x as the next term, which is the nth plus 1 derivative computed at a over n plus 1 factorial x minus a to the n plus 1. So see, this plus 1 everywhere is just telling you that if you're using n terms for a Taylor polynomial, the nth plus first term, so the next term, is the one that contains most of the error. And that's it, right? So you are computing that. There is the proof in the textbook, obviously, if you're interested in that. Since, again, not honors version of the class, so if you're interested in that, you can read the proof. It really doesn't require an example because you know how to compute this term. Well, just plug 4 everywhere, right, for the error in this particular problem. Or plug 5 to calculate the next term, right, and so on. Now, before we end, I just want to go back to this calculation here. Observe how when we used 2 terms, right, this was a linear approximation, so function and a first derivative, so that's 2 terms. We got 9.7, and then when we introduced the third term, right, we got more precision to it. So technically, there is this 0.045, right, difference between these two together, right? There's your error, right? The most error, if I'm to use these two, most of the error is within this. Now you see it's a very tiny number, right? Which should make sense. So that's the story on introductory story on power series. In short, the goal is to take a function and change that function into a polynomial, and then calculus is like this once it's in a polynomial form. What's 9.4? 9.4 is literally write the function in this fashion and then take the derivative of it or integrate it. That's technically what it is. That's your 9.4. So I'm literally going to spend 3 minutes on 9.4, and that might as well happen next class, you know, on Tuesday. We might be done with chapter 9. Monday, that's what I said, please pay attention. Okay, so end the stream, and I have that question that we have to answer, and then we leave.